highest degree term there, and don't just assume it's always that lead power. Always look for them all down the line there to see which gives you the highest power. All right. And again, this is not new, right? I think you guys have talked about this kind of stuff before, but there's kind of two things that we use to help judge the end behavior polynomial. You know, what happens as you go really, really, really far to the right, and what happens as you go really, really, really far to the left. Okay. So two things to kind of judge that for right now. The one is the leading coefficient. Okay. And then the other thing is the degree. And that's when we're dealing with polynomials, okay? That's the end behavior for polynomials only, right? You may remember such things as like horizontal asymptotes, right? But with a polynomial will never have a horizontal asymptote. It's only when you start dealing with rational functions, that's when you have a polynomial divided by a polynomial, okay? Which is called a rational function. When you have a polynomial over a polynomial, that the whole thing is no longer a polynomial, right? But just a straight up polynomial by itself, you know, those two things, lead coefficient and the degree, determine end behavior. So, leading coefficient and degree of the polynomial determines the polynomial's end behavior. And so I'm going to make a little table here to kind of help organize things. All right, and the way we'll say this is, well, I don't know, I'll do we'll do it this way. So, if the degree is, and I'll put odd here, and then I'll put even here. Okay, and so we'll make like a little table here from this. Let's see if I can get this to like be okay. There we go. And then we'll also say if the lead coefficient is, and then I'll put that there. Okay, and we'll say positive here. And then we'll put like negative down here. I'm going to separate this. Okay, maybe I need to put some more. So you have four different scenarios. Okay. If the degree of the polynomial is odd and the lead coefficient is positive, one scenario. If it's even and then positive, another scenario, odd and negative, one scenario, and then even and negative, one scenario. Okay. And the way that we are going to be describing our end behavior, right, again, is using the idea. So again, end behavior, it's what happens as x approaches infinity, right? Because what is that representing? As you go really, 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 really far to the right, going farther and farther and farther to the right, your x values are going further and further and further. They're increasing, right? More and more and more, they go towards infinity, positive infinity, right? So as x goes to infinity, and then likewise, we want to be able to describe as x goes to negative infinity. That would describe going really, really, really far to the left, right? Because negative infinity is in the left direction there. And we want to be able to describe what's happening to our function. So as x approaches infinity, f of x, the y values, that's the end behavior. Okay, so what will they approach? Okay. Well, for an odd degree, bless you, with a positive lead coefficient, as x approaches infinity, f of x will also approach infinity. And as x approaches negative infinity, f of x approaches negative infinity. Okay. And I'll draw just a little example of this. You know, so for example, like a cubic function. Okay. Okay. Some sort of cubic function there. There's an example. As you go further and further right, the function, as we go further and further right on the function is going to increase and increase and increase without bound. As we go further and further left on the function is going to decrease or go down, go towards negative infinity. Okay. There's that. And so then for the second situation where we have an even degree but still a positive lead coefficient, as x approaches infinity, f of x will approach, well, infinity. And as x approaches negative infinity, f of x will also approach positive infinity. Okay. An easy example here is like the graph of, just think of the graph of like y equals x squared, right? As you go further and further to the right, it's going to go up, but as you go further and further to the left, it also goes up there too, right? So the end behaviors are the same. Now, if we take this odd degree polynomial that has a positive lead coefficient, and then we keep it an odd degree, so the shape will still be basically the same, but then have a negative lead coefficient, what kind of thing will result here? What's going to happen? What kind of transformation is going to happen? Yeah, it's gonna reflect. Okay, it's gonna reflect. Okay, it's gonna reflect. And so what that means is that now we'll still say as x approaches infinity, but where f of x used to be going up, now it will be going down. So now f of x is going to approach negative infinity, right? And then as x approaches negative infinity, now f of x will approach positive infinity. So yeah, it just kind of like it flips the behaviors. Okay. Now as we go far to the right, we're going to go down. As we go far to the left, it's going to go up. And again, you can, kind of draw a little example there or something. Okay. And then by similar fashion, as x approaches infinity here, f of x will now approach negative infinity. And as x approaches negative infinity, f of x will also approach negative infinity too. So you can expect something like that, right? So there are your different combinations, right? If you have an odd degree but positive lead coefficient, it's going to look like that, right? If you have an even degree and a negative lead coefficient, there's your end behavior. Okay, any questions on any of that? All right, then I'm going to give you guys, well, we'll do two together, and then I'll have you guys try some here. Okay, so we'll do two together. So now we've got that little chart to help us. All right, let's go and let's determine the end behavior for each. Determine the end behavior for each. So, number 1. F of x equals negative x cubed plus 4x. Okay. And before we even need to start thinking about this, we know that we're going to have to describe the behavior as x approaches infinity, and we'll have to describe the behavior as x approaches negative infinity. Right? We got to say what happens if x is going really far to the right, and what happens if x goes really far to the left. All right. So, what's the degree of this polynomial? It's odd, okay, it's 3, right? So it's odd, okay? And then what's the lead coefficient, positive or negative? Negative. So we got odd, negative lead coefficient. So then as x approaches infinity, we'd expect that f of x is going to approach negative infinity. Okay? And as x approaches negative infinity, we'll expect that f of x will approach positive infinity. Alright. And again, the beauty of this right now, since we're not, on a quiz or a test, and this is not a non-calculator section or a calculator section, we can check. So negative x to the third plus 4x. No, it's in y too, but okay. Does that match? Does our behavior match here? As x approaches infinity, as we go farther and farther to the right, sure enough, our function value is going to negative infinity. As we go further and further to the left, sure enough, our function value is going to positive infinity. Okay, so that's right. Hooray! All right, let's try another one. G of x equals 3x to the fourth minus 5x squared plus 4. Okay, so as x approaches infinity and as x approaches negative infinity, so, Morgan, what's the degree of this polynomial? 4. Very good. So that means it's an even degree, right? Okay. And let's go to Andrew W. What's the coefficient here? Positive or negative? Positive. That's right. Okay. So we've got an even degree, positive lead coefficient. So as x approaches infinity, f of x will approach what, Brian? Positive infinity, you got it. And as x approaches negative infinity, what will f of x approach? Positive infinity as well. Very good. Okay. Those even degrees, right? Their behavior is the same. The even degree polynomials, their behavior is the same. So if one goes up, the other one's going to go up. If one goes down, the other one goes down. Okay. I feel like this is a little teapot here. Okay. So anyway, there's the end behavior. Yes. Very good. All right. Let's have you guys try to here. Okay. Just take like 30 seconds here and evaluate it here. H of x is equal to x to the fifth minus x. Okay. And f of x equals negative 13x squared minus 2x minus 5. Alright, let's go ahead and find the end behavior of those. Describe them. You will need to be able to come up with this end behavior statement. Okay? I'm not going to have just blanks for you to fill in. It'll be more along the lines of what you see here. Well, you should be able to. I may have blanks for you to fill in. I'll say that. I may have blanks for you to fill in, but you should be able to come up with this statement on your own. Okay? You should be able to come up with them on your own, right? So, yeah. I may prompt you with blanks to fill in, but you should also be able to come up with them on your own, too. So. Jackson, what'd you get for number 3? Okay. And then? Okay, very good. Yep, sounds right. And how about Julia R? What do you get there, Julia, for number 4, the end behavior? Mm-hmm. Yes, and so if you weren't able to follow along with all that verbal description there, there's the end behavior written out too. Okay. Questions on end behavior, right? Stuff you guys seen before, review. So, but if you have questions, that's okay still. All right, just make sure you got those down. Okay, so let's take a look at some polynomials then, and about how I would like you all to go about trying to sketch the graph, okay? And again, it's helpful because, like I said, you know, we'll have calculator sections of our test, we'll have non-calculator sections. This kind of question will more than likely be on a non-calculator section because a calculator would just make it trivial. And of course, then you guys are all like, well, but when are we ever going to not have a calculator in real life? I understand, you're right. But it's helpful to have a comprehension in your own mind of something because the calculator is only as smart as you are. It will do things for you, but you need to be able to interpret them. And maybe one day the calculator will actually be smarter than we are. I don't know. Like, there'll be artificial intelligence, and then, you know, Skynet will take over, and we'll just all be killed by androids. But that's okay. I'm replaced by androids, but, you know. Not yet. Not yet. All right. So let's just jump right in with an example here. And we'll do g of x equal to x times x plus 2 times x plus 4. So I'm going to kind of like start with a very nice polynomial. Okay, start with a very nice polynomial here. Okay, it's already factored for us. Of course, we know how to factor, right? So I mean, if this thing was not factored, we would, you know, try to factor if we could, just to help things out. And so some of the things I'm looking for when we do a polynomial. So helpful things. First thing we want to probably try and do is find the zeros. Okay, which would be like the x-intercepts. All right, alternatively or synonymously in doughboy. There we go. I missed an R in intercepts, so now it looks really out of place, but that's okay. It's there. All right. We're going to find those zeros. Okay. And then, of course, we have, like, peaks and valleys, right? We have, you know, maximums and minimums, or relative maximums and minimums between those zeros, typically, right? What goes up must come back down in order for us to get to another zero and stuff. So when we find zeros, we also want to, like, evaluate the behavior between zeros. Again, we may be tempted you know, we may be tempted to just think it alternates, right? If it was coming from the bottom, it might come back up, and then, you know, kind of thing. But it doesn't always just alternate straight up, so we have to be careful with that. Okay, so that's like the middle behavior there. And then, of course, you want to evaluate the end behavior. End behavior 2. And then finally, we'll just sketch graph. Okay. And that will be kind of like a good way to get down the important piece of information for polynomial. Okay. Notice I don't say find the y-intercepts here. If you want to find the y-intercept, feel free. Okay, you can also find the y-intercept there too. But you know, this is the kind of stuff that I feel like is, you know, pertinent at least, right? So let's go about doing that here. So let's first find those zeros. So that means we're going to set our polynomial here equal to 0, right? And so it's pretty obvious here by the zero product property, our zeros are going to be x equals 0, x equals -2, x equals -4. We just set each one of those equal to 0 and solve. And then, so that was like 1, here we'll do 2 here. So the behavior between the zeros. So what I like to do is kind of like line these zeros up in order, okay? So list zeros in order. Okay. So like the -2, 0, whoops, -4, -2, and 0. And then just pick a point between. I like to pick the midpoint, but you don't have to. Okay, I mean, you can kind of just pick some points between there. But I like to pick the midpoint. I think it gives us like the best kind of idea, you know, of how high it might go. So, you know, obviously midpoint between -4 and -2 would be -3. And the midpoint between -2 and 0 would be like -1. Okay. And so then these are x values, right? But we're not just interested in, you know, the midpoints. We want to know, like, you know, how high or low are they? Like, what are the actual coordinates of these points? Okay. What are the actual coordinates of these points? So we're going to take these two x values and get their matching y values from the function up here. So we're going to, you know, evaluate that g of -3. We're going to evaluate, you know, g of -1. Okay. And so that's going to be, let's see, it'll be -3 times, let's see here, -3 plus 2 will be -1, and -3 plus 4 is +1. And then for g of -1, it'll be -1 times -1 plus 2 is 1, and -1 plus 4 is 3. So we get 3, which is then the point -3, 3. And here we get the point, well, sorry, that was -3, so you get -1, -3. Okay, so we have some zeros. We have some points between those zeros to know whether we're going to go up or down between them. And then finally, we want to evaluate that end behavior before we do our sketch here. So I'll just do that part right here. Okay. So the end behavior. I call, like, by the way, this step right here where we kind of evaluate what happens between the zeros, I sometimes call that like the middle behavior. I'll probably refer to that as the middle behavior. That is not a mathematical thing. You know, it's not like if you go and talk to some other people and like, oh, the middle behavior. I mean, they'll probably understand what you're talking about, but it's not like a, you know, a thing. It's like what happens between the zeros. End behavior, right, is a thing. And so let's evaluate that. So we have to write as x approaches infinity. And we have to determine as x approaches -infinity, what is happening to f of x? What is happening to f of x here? Okay. So, to do that, right, we need to know the degree and the lead coefficient. So, what is the degree of this polynomial? 3? Wow, but all I see here is x to the 1, x to the 1, x to the 1. Why are you getting 3? Because you multiply it out. Exactly right, right? This thing, right, when it's factored like this, is not in like the appropriate form. We can't tell the degree because it's not all multiplied out. If you were to multiply this out, okay, we don't need to multiply the whole thing out. Like, you don't actually need to do x plus 2 times x plus 4 and then distribute the x. So you can kind of like, you know, just mental math this and see, okay, it's going to be x and x and x. They're going to multiply together at some point, give us x cubed, right? That's the highest power we're going to get. So yes, it's a odd degree. So degree is 3, and then what will the lead coefficient be? Positive, right? You can even more specifically say 1, right? Because it's going to be a 1x times a 1x times a 1x. So the lead coefficient is going to be a 1, positive 1. So so lead coefficient positive. Okay. So degree 3, positive lead coefficient. That means as we go really, really far to the right, our function is going to go up towards infinity, and as we go really, really far to the left, our function is going to go down towards negative infinity. So positive infinity, negative infinity there. Okay. And so with all those pieces, we can finally do a little sketch here. So that's what I'll do. I'll just squeeze it in right in here. Excuse me. Okay. All right. Let's see. 1, 2, 3, 4. Right. A few things to remember again, right? If you don't label your x and y axis, I will assume you're counting by ones. All right. If you don't label your x and y axis, I will assume you're counting by ones. Also, your scale for your x-axis must be the same across the entire axis, right? So every once in a while, I'll see students like count by 2s on the x-axis, but then on like the positive side of the x-axis, and then start counting by 1s on the the negative side of the x-axis for whatever reason. Okay, you can change the scale from the x to the y, right? So the x you can count by 1s, and the y you can count by 2s. However you want to do that, that's fine. But you can't change different parts of the axis. One axis is can only count by one, quantity there. You can't change that amount. All right. So let's plot these points here. So we got our zeros at -4, -2, and 0. Excuse me. And then we have our middle behavior, -3, 1, 2, 3, 3. Okay, and then our middle behavior here is -1, -3, 1, 2, 3. Okay, like that. And then end behavior, okay, to kind of give yourself, to give yourself an idea about what to do here, I like to go to like the furthest right point. So as x approaches infinity, so like the farthest right point is right here. As x's go even further to the right, as our x values go further to right here, the function is going to continue to increase. So you can like just draw like a little arrow there to kind of help guide you. It's going to go up. Right, and then as x goes to negative infinity, so now we're going to go furthest left, as our x values go further and further left here, the function is going to go down. So I'm going to put that right there. And you just want to connect the dots from left to right, right? So I go whoop, and down, and up. You can do something like that. Okay, whatever you want. There's the graph. Okay, connect those dots, and that gives us a nice sketch. Without needing calculator, of that polynomial there. Okay. Any questions on any of that? Any questions on any of that? Okay. So I have one for you guys to try, and then we'll get you started on the assignment. Okay. So we're just about done here. Okay. Before I do move on, though, I do want to point one thing out. If you go to graph this thing on your graphing calculator. Okay, there is the graph on your graphing calculator. And if you look at this, and you look at this, you're like, wow, we did a really good job. Why do we even need a graphing calculator here? Because the graphs look exactly the same, right? They have the same zeros and the same end behavior. It looks like the same, maximums and minimums. Well, if I go to second trace, and if I go to maximum, okay, I'll go to the left of my little maximum here, the right of my maximum. This is actually called a relative maximum, and I'll go towards the top there for the guess. When I actually calculate that maximum value, it does not occur at -3, and the maximum y value is not just 3, okay? So, what's the deal here, right? Well, again, that's why we're calling this sketching the graph of the polynomial, okay? It's not precise. Right? It doesn't happen that the midpoint between zeros will always yield the maximum or minimum value. It will give a good guideline, right? We get a pretty good, accurate picture of it, but it's not precise. And again, we don't have the skills right now to do this by hand precisely. In calculus, you will acquire those skills, and you'll be able to precisely determine, what the value of that, x maximum would be, and the same thing for the minimum there too. Okay, but right now we don't have those skills. All right, so we have to be satisfied with this. All right, so here's one for y'all to try. So try this one. We'll say f of x equal to -2x squared times x minus 2 times x minus 6. Alright, so I want you to, again, zeros, behavior between the zeros, the middle behavior, the end behavior, and then sketch it. Okay, so I'll list that out here for you. The zeros. By the way, folks, zeros can be spelled with or without an E. When you have the plural there. I think I'm really using the inappropriate one. It should be Z-E-R-O-S, I think. But anyway, I put an E in there. Behavior between zeros. Okay. Did that bother someone that I was using an E in my zeros? No? Okay. I wasn't sure. Just FYI. Alright, so there you go. So go ahead, find those pieces of information, and sketch a graph, please. Don't use your calculators. You can check it at the end, but do it without a calculator, okay? Do it without a calculator. And again, if you need to, check your calculator. If you're like, wait, what's going on here? But try without first. Try without first. What's that?
Like 128. Yeah.
Negative equations, they're both gonna go. Yeah, you're in.
I didn't know if we had to do that.
Don't forget to include that end behavior, right? Like draw those little like help arrows at the end if you need to. Middle plus two. Yes, this looks good. The 4, it shouldn't be down here. The 4, it should be something over here. Yeah, that looks good.
I'm tired of that.
You understand this stuff okay? Yes. Yeah, so you can just like, if you don't want, you can like, just so that it goes off the thing. Kind of like so behavior 1 is kind of between there, so 1 minus 2 would be negative 1. So it would be, negative 1 to positive 2, and then that would be negative 5. And negative 10 to negative 10. Yeah, it's a negative, and negative, and negative. So it's a negative 10. Yes. Yeah, exactly right. Something like that. Oh, what? Oh.
Yeah, but that's like 6.
You just kind of sketch. And like,
I mean, do the X scale.
why?
Yeah, just get the basic shape.
I did the arc with arrows.
Or when you get all your points together, you can kind of get an idea like what kind of scale you may want to use, right? Since you know you have to have this huge Y value, you may want to adjust your scale accordingly too.
He's a math teacher. He's willing to grade it, so I thought it was nice.
No, but I mean, what you're saying is not wrong either. I mean, I can see what you're trying to say. That works too. I mean, but if you want to be able to include all the graph on there. It works. It's just that you have a really shallow then kind of bottom point there, since it's only.
It was very much about
Right here, what you want to do when a polynomial multiplies like this, just hit the zero, break up your zero, break up like number line, give it a zero, and then have the point for each interval back to the all. Yes. Yeah, that's right.
We still have our home.
No, you're right. You're an opposite. Correct. So where did you go? And then down. You got it. Exactly right. Yep.
Yes. Okay. So here is what your graph should look like. Something like that. Okay. So of course I take all the nice easy ones to do for you guys, and then I throw something like this at you. Okay. And I feel that's okay, because why not, right? Okay. So a couple things that happened here. First of all, right, we had like a really weird scale, right? Okay. When you looked at your like zeros, those weren't too crazy, right? But then when you did the behavior between those, you know, we had a -10, which isn't too bad, but then 128 was that y value if you use like the 4 between the 2 and the 6 there to help you guide you. So 128. So that goes up pretty high. So you know, you may want to consider your scale here. I'd count it by tens. Okay. And then as far as the end behavior goes, right, since we have, let's see here, an x squared times an x times an x, that's going to be x to the 4th, so it's degree 4, even degree, but then the lead coefficient is going to be -2 times 1 times 1, so it's going to be a negative lead coefficient, so that means both end behaviors are going to go down. And so when you go and plot the points, and you go to sketch it, it doesn't follow that typical behavior that we would expect, right? Typically we expect, okay, we go up through the 0, we go back down through the 0, we go back up through the... Oh, it doesn't go up through the 0, it comes up and touches the 0 and goes back down. Now, is there something about this polynomial that would maybe indicate that to us? So is there something about this polynomial that indicates that maybe we should expect at 0 here to come up, hit that 0, and then go right back down and not go through? Is there anything about that? Yeah, Andrew? It's the x squared. Yeah, that 0 is a double root. It occurs twice. Okay, whereas, you know, this 2 and this 6, they're both single zeros, right? That 0, double zero at 0, and so that results in that kind of behavior. Okay, so when you see something like this, be on your toes, right? That you're gonna maybe just kiss the axis, right, and not actually like go through it. Okay. One other thing I wanted to mention too, you know, keep in mind, you know, if I were to do something like this, put a square there, all right, what is the degree now of this polynomial? What would it be? If I threw a little 2 in there like that, what would the degree of that polynomial be now? 5. It would be 5. Yes, very good. It would be 5. Okay. Even though we see an x squared, we see an x here, it would still look like x to the 4th, but this x minus 2 is being squared. So it means this x will get squared, and so it's really like an x squared times x squared times x, so it's like an x to the 5th. So be on the lookout for that too, right? I'm going to be on the lookout for that too. All right. Questions on any of that? Okay. All good? All right, let me give you guys your assignment then. Here we go. It's going to be on page 145 in the book. Page 145, numbers 9 through 16. 21 to 25, the odds for those, and then 79. Okay. So some of these will just be evaluating end behavior. Some of these then may also be graphing and stuff too. So don't think that those are all just going to be a bunch of graphing problems. Yes?
Are the 9 through 16, is that also odd, or is it
Just the ones in the parentheses there are odd. So 21, 23, 25, I guess, is, you know, yeah. But 1 through, oh my goodness.
I'm just gonna throw this out and I'll be right back.